Hello and welcome back to Unbounded Operators, the video series where we talk about infinite dimensional Banach and Hilbert spaces and operators on them. And in today's part 11, we look at the adjoint operation we have for operators, and in particular, we look at the double adjoint. However, as always, before we write down today's theorem, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And there you might already know that Steady supporters can download a lot of additional material with the link in the description. For example, you can find PDF versions, quizzes, and early access to all new videos. And then I would say, let's immediately start with the topic of today by considering two Hilbert spaces X and Y. And we take Hilbert spaces because I want to look at the Hilbert space adjoint. This means we consider a linear operator between X and Y, which could be unbounded. And then we have already learned that the adjoint of T star is well defined if T is densely defined. And there please note that now T star goes from Y to X. And then in the case that T star is also densely defined, we can form the adjoint again. In other words, now we just have T star star. So this is the double adjoint, and as the operator T, it goes from X to Y. Therefore, it definitely could happen that T star star is the same operator as T, which actually means that it acts the same way and it has the same domain as T. But there I can already tell you, this is not always the case and definitely something we can discuss now. So we definitely have some questions to answer here. For example, is this double adjoint always well defined? What is the domain of T star star? And what is the relation to the original operator T? And now it turns out that we really have nice answers for closable operators. This means for the theorem here, we need two assumptions for our operator T. First, we want a densely defined operator, which means that the domain of T lies dense in X, because only then the adjoint of T is well defined. And then the second assumption is that T is a closable operator. And then we immediately get the result that T star, the adjoint of T, is also densely defined and closable. In fact, we have even more, namely T star is already a closed operator. However, the important part for us is that T star satisfies all the assumptions we had for T, which means we can just form the adjoint again. Which means that the double adjoint T star star is a well-defined closed operator as well. And there you already see, because it's closed, it cannot be equal to the original operator T in general, because T does not have to be closed. Therefore, the actual operator for the comparison should be the closure of T. And the standard notation for that is T overline. And there you might already guess, T overline, the closure of T, is exactly T star star. It's the same operator, which means they act the same and they have the same domain. Or in other words, they have exactly the same graph in X times Y. And in fact, we will work with the graphs in our proof here. So please recall, our graph GT consists of the pairs in X times Y, where X comes from the domain of T and Y is the image of X under T. And now, since by assumption T is closable, we know that the closure of this graph is a graph again. And by definition, the corresponding operator is the closure of T. So we can write that this is the graph of T overline. So you see, in order to write down the proof here, we actually should work in the Cartesian product of X with Y. And there it's not hard to see that X times Y is actually also a Hilbert space. We have that if we change the standard norm on X times Y a little bit. However, it will be an equivalent norm, so it will not change the closure here, for example. And as you might already guess, the whole definition is quite simple. We just have to write it down for two pairs. So let's say we have xy and x tilde y tilde. And now the inner product here in x times y is just a combination of the two inner products we already have. So first we have our inner product in x, so we combine x with x tilde. And then we just add the inner product in y. And that's it. This is the inner product, and it makes x times y to a nice Hilbert space as well. And this tells us that we can also look at orthogonal complements in this new Hilbert space. So we can use the whole Hilbert space theory, which tells us that the closure of U in the orthogonal complement does not change anything. And moreover, the orthogonal complement is always a closed subspace in x times y. So please note, we have discussed all of that in my video course about Hilbert spaces. For example, there we have also discussed that double the orthogonal complement for a closed subspace gives us the original subspace back. Hence, in the case that the subspace is not closed, we just get the closure. This is clear because the orthogonal complement cares only about the closure anyway. And now, of course, this is what we want to apply to our graph of T. So this means using 2 times the orthogonal complement on GT gives us the closure. And now we already know that this is actually a graph again. And there you might already see that this is actually the meaning of our double adjoint is equal to the closure of T. But honestly, this is not clear at all yet, because we first have to discuss the relation between the orthogonal complement and the adjoint of T. To see this, let's first write down what the adjoint does in the inner product. If we take ytx as an inner product in y, then we can transform this to an inner product in x by using the adjoint of T. So there we have T star y with x in the inner product of x. And this equation holds for all vectors in the corresponding domains. And now we want to reformulate that such that an orthogonal complement comes in. Which means we just need a formula with an inner product that is equal to 0. And it's easy to do that by just bringing the inner product with x to the left hand side. And then we have the 0 on the right hand side. And then also the minus sign here on the left we can bring into the inner product. And then what you should recognize with this addition here, we just have the inner product in x times y. In other words, we already have described an orthogonal complement in x times y. To make this clear, maybe let's write it down with 2 pairs. The first one here is the pair consisting of minus t star y together with y. And then the second entry is just x together with tx. And this is the inner product, and it's equal to 0. And there you should recognize that the second term here, xtx, is just the graph of T. So we actually have that the first pair here lies in the orthogonal complement of GT. And this is correct for all vectors y in the domain of T star. And now you should see that this pair here almost describes the graph of T star. So the only thing we have to do here is to flip components with an operator v in x times y. So it's quite simple because it just tells us that every element xy gets flipped in the components. So we send xy to the element yx. So formally we have 2 different Hilbert spaces on the left and on the right here, but you can already see they carry exactly the same information. So it's a really simple linear operation where the inverse is also clear. And by using this inverse of v, we can reformulate this equivalence again. Namely, we have v inverse applied to y with minus t star y. So we actually talk about the operator minus t now. Or more precisely, what we have here is the graph of minus t star. So actually what we get here is a relation between 2 graphs. So on the left hand side we have the graph of minus t star, and then we have a set inclusion where on the right hand side we have the orthogonal complement of the graph of T. And the equivalences tell us that this set inclusion is always correct because the formula from above is always correct. And now it turns out that we also have the other direction of the set inclusion, so we actually have an equality here. So this is a formula you definitely should remember because it gives us the relation between the orthogonal complement and the adjoint of T. And now if you want, we can also quickly explain the proof of the other set inclusion. There you would take an arbitrary element from the right hand side, so an element from the orthogonal complement. And to keep it simple, let's say we have x tilde and y tilde. And since they are in the orthogonal complement, we know that the inner product in x times y is equal to 0. So as before, we know that the addition of the two inner products has to vanish. And the graph of t tells us that this has to be correct for all x in the domain of t. And moreover, as before, we can also subtract one inner product and bring this to the right hand side. Then we have x tilde on the right hand side together with a minus sign. And now the important thing is that this equality holds for every x in the domain of t. And there we immediately recognize the definition of the adjoint of t. We get that y tilde lies in the domain of t star, and the value of it is given by minus x tilde. So more precisely, t star of y tilde is equal to minus x tilde. And that's actually all we need, because now we can substitute x tilde in the pair. So the pair is of the form minus t star y tilde together with y tilde. And there you recognize the same form as before, so this lies actually in the set v to the power minus 1 of g of minus t star. So it's an element of this set, and that's what we wanted to show. Okay, so this is really nice, because now we have this identity for the two graphs. And this immediately tells us something for the graph of the adjoint of t. Namely, the graph of the adjoint is just v times the orthogonal complement of the graph of minus t. And since we know from the Hilbert space theory that orthogonal complements are always closed, we can also conclude that t star is a closed operator. Which means now we have proven one of the claims in the theorem. And there you see, this claim does not need that t is a closable operator. However, we need it for the second claim, namely that t star is a densely defined operator as well. So the question we want to answer now is the adjoint densely defined. So we need to show that the subspace dt star lies dense in the Hilbert space Y. So the closure of this set should be equal to Y, but this means that the orthogonal complement is only the 0 vector. So this is what we want to show, so let's take an arbitrary element Y from this domain. So by definition, this means that y combined in the inner product with any element from the domain is equal to 0. And now if we want, we could arbitrarily rewrite this as an inner product in x times y. Then we could just take the element 0y together with the pair t star y tilde y tilde. And there you see, this last pair together with the v operation gives us the graph of t star. So we just have to flip it to put the pair in the correct order for a graph. And now what we see is that this inner product is equal to 0, which means that 0y is orthogonal to the graph of t star. Or to say it more precisely, 0y lies in the orthogonal complement of v to the power minus 1 times gt star. And there we can just use what we already know of gt star, namely it's v times this orthogonal complement. So actually we have a double orthogonal complement. And this is quite simple in a Hilbert space because it just gives us the closure of the subspace. And there we can finally use that t or minus t is a closable operator. And indeed here it does not matter if we have minus t or plus t, because it only matters that we have a graph of an operator here. Simply because we know that an operator, a linear operator, sends 0 to 0. So the only possibility for 0y lying in the graph of a linear operator is that y is equal to 0. And exactly this is what we wanted to show, because it means that the domain of t star lies dense in y. So now we have also proven that t star is a densely defined operator. And as you might recall, this is a really nice result, because it means that we can also form the adjoint of t star again. And this one is what we simply call the double adjoint of t, and it should be equal to the closure of t. So we know that the graph of the double adjoint is well defined, and we can use all the formulas from above. Indeed, we know the relation between the orthogonal complement and the adjoint. So for example, from above we now know that we have the graph of minus t star. And if we form the orthogonal complement and flip the components in the correct way, then we have the same graph. And now we can simply apply this formula again for minus t star. And since we have 2 times a minus sign, we just get t. And now at this point you should note that flipping the coordinates before or after the orthogonal complement does not change the result. It's really easy to show, and as you already know, v does not change any information at all. So flipping 2 times will cancel here, and what remains is the double orthogonal complement. And by assumption we already know this is the closure of the graph, which is the graph of the closure of t. So most importantly, here it tells us that the graph of the 2 operators is exactly the same. So by definition, this means that the 2 operators are exactly the same in acting and domain. So we are allowed to write an equality of densely defined operators. And with that, the whole theorem is proven. And please note, in particular, the theorem tells us that for a closed densely defined operator t, the double adjoint is equal to t. So this is a really nice result for the Hilbert space adjoint, and I would say let's discuss more about that with the next videos. Therefore, I really hope I meet you again and have a nice day. Bye bye.